Hello, everyone. My name is Logan Selph, and today we're going to be covering our new multi-wavelength NeRF model geared towards modeling spacecraft in shadowed environments. Now, before we begin, I want you to consider the task of collision avoidance and risk assessment. Imagine that you are a spacecraft operator, your spacecraft is orbiting the Earth, and you have to consider the different things that could potentially collide with it and damage it, like other spacecraft or debris or really anything else that you could think of. Now, in this situation, you have a couple of things going for you. The first is that you at least know something's there. If you're worried about something, it likely means that it's being tracked. You know roughly where it is and just about when it will reach you. And you have something you can do to save your spacecraft. Sometimes this means moving it completely out of the way. Other times, in plenty of the times, this means that you can at least change its attitude such that it was safer than it was before. You can rotate the spacecraft so that it's a little bit less likely to end up in a collision. Now, you have some things going against you too. The first is that you have to react quickly before the object reaches you. And worst of all, you likely don't know the shape or true size of the object that you're working with. In the common case, where you can only rotate your spacecraft, change its attitude, this puts you in a very bad position, since you're just about as likely to rotate into a position where you're in danger compared to a position where you're not in danger anymore. So it's for reasons like this and plenty more that you could imagine that we want to know how we can provide fast and accurate shape models to spacecraft operators so that they can assess their situations a little bit better. Now, before we get into the NeRF modeling aspect of this, we need to talk about a couple of popular reconstruction methods. The first is structure from motion. This uses simple stereo parallax and triangulation in order to generate a point cloud of the object that we're trying to model to define its geometry a little bit better. This is fast, but in the case of point clouds, this is not continuous, and it can create models that suffer from holes, especially on low feature surfaces or reflective solar panels. So it struggles a little bit with spacecraft in general. The next most popular is stereophotoclinometry, which has been very successfully used to map many of the planets and celestial bodies in our solar system, and has been used for navigation on missions such as OREX. Now, a very basic way of how this works is you have an initial crude digital terrain map. As you get closer to the object, you collect images of it, and you refine this digital terrain map by combining the methods of simple stereo parallax, like structure from motion, and photoclinometry, which extracts features from these images between comparing their different lighting and shadings. You repeat this over and over again until you reach a really excellent quality model. Unfortunately, this requires a lot of data and is very computationally expensive. This is where we get to neural radiance fields, which are neural network representations of the underlying radiance field occupying a scene. These are excellent quality, very fast and lightweight, and require very few amounts of data, on the order of dozens of images in order to get really good quality models. Now, we don't have too much time to get into the full makeup of NeRFs or get too deep into it today, but I can give you a good high level view of how they work. First, you collect a training data set of images and poses. The poses are the positions and viewing directions for each one of the images in the scene. Next, you use this training data set to train the NeRF model. And then, after the model has been trained, you can take any pose that you haven't necessarily visited before, input it into the model, and the model will generate the corresponding image from that pose. Essentially, what we have is a model that is fully continuous, excellent in quality, and can quickly give you any image from anywhere you query in the scene. Now, now that we know a little bit about what NeRFs are and how they work, how do they perform with space-based observations? Well, in order to explore this, we're going to be using a training data set from our Hubble model. This training data set includes 5 distances from 50 meters to a kilometer with 614 images per distance, all using just one single sun angle. Now, we have a distribution shown here with these polar plots that shows for a single distance for 614 images how our data set is spread out. It's spread out over a spherical grid, roughly evenly between the two hemispheres. And when we train a model using this training data set, we get a pretty good visual output. You can see very good detail on the reflections on the spacecraft. one of the solar panels very dimly lit. And overall, the structural detail on the surface of the spacecraft is pretty good, as along with like other shadows cast into the scene here. Now, I was a little bit specific with my wording on how this is good visual performance. You can see this in the first two columns here too, between the ground truth and the NeRF renders. It has good visual performance. But if you look at the depth field, you see a different story. The depth field here is the NeRF's output of its representation of the underlying shape model that it's learning. And as you can see, especially in case two, it is incomplete. Half the spacecraft is just about missing. And this is to be expected. We have very severe shadowing, especially as you can see in case two and case three, where half the spacecraft, or in some cases all of the spacecraft, is just about indistinguishable from the background. This means that when the NeRF is training on it, it has nothing to do to discern the shape in these shadowed regions. So, in the worst cases, it says there's nothing there. Or, as you can see in other parts of the image, it has a little bit of a hard time trying to tell what's there, and it starts accumulating points, these points of density where there should be nothing. Now, as this is expected, this is not what we want to see. And even in the worst cases, this can cause the model to diverge and just become completely useless. So this has given us some evidence that NeRFs struggle with shadows, and it's something we want to solve because we need these full underlying shape models in order to correctly assess these objects. So how can we develop NeRFs that are robust to complex lighting? Well, we propose MW-NeRF. This adds an additional network to the traditional NeRF architecture, which allows it to learn scene representations from two different data sets at the same time. These two data sets are supposed to have been taken from different wavelengths. In our case, we're using optical and infrared, and they'll learn a color representation for each at the same time individually, while both sharing the same underlying density field or the same underlying shape model. So essentially what this does is this allows us to train a model that can optically represent the neural radiance field while still benefiting from the extra shape information you can get at other wavelengths, such as infrared, where the model will be emitting the light rather than relying on the sun for illumination. And in our first pass through MW-NeRF, this is exactly what we see. So on the left, we can see the same plot that we had before, where half the shape model is missing from this visually only trained NeRF. On the right, we have MW-NeRF trained on both optical and infrared data. And we see from our depth map that not only is the shape model fully recreated, we see that detail is much finer than it was before, even in parts of the image where it was optically visible before. We see the extra points of density that were accumulating on different parts of the spacecraft before are now gone. And we see in the visual representation between both of these models, both of them are performing excellently. They are very hard to tell apart just by viewing it with your eye. And overall, we get a new NeRF which can learn excellent visual representations while still retaining that amazing underlying shape model. Now, we want to get a little bit into the quantitative results here, but before we can, I want to talk about the performance metrics we'll be using. The first is the structural similarity index measure. This is very simple. On a scale of 0 to 1, it will assess how structurally similar two images look, 1 being the best and 0 being they don't look the same at all. The second will be total intensity percent error, which is simply the percent error between the total sum pixel values between the two images. We've included this one because it is a little bit easier for new time viewers to interpret compared to SSIM if you haven't seen that one before. In order to visualize this polar plot, in order to visualize these performance measures, we've decided to go with the same polar plots that I used to describe the training dataset layout. So for each one of these training images, we've calculated the NeRF rendering for it, compared them in order to get both of these metrics, overlaid each one of those values onto the same polar plot, onto the same grid as we've seen before with the training dataset, and we interpolated in between them to get a fully continuous heat map describing these metrics in this polar plot form. So We can see the comparison between the two here. A quick rule of thumb, the top images are the percent error, where brighter values are the worst performing. And in the bottom, we see the SSIM, where the brighter values are the best performing. And we notice a few things right off the bat. First, the visual performance between both of these models is very similar. And for the first pass of MW-NeRF, this is good. We wanted to at least retain that previous visual performance while getting these shape models. We see a little bit of some brighter spots in the MW-NeRF case. This is because these are in the shadowed regions of the training data set, where the total sum of the ground truth images are a little bit closer to zero. So when the MW-NeRF has a little bit of a hard time separating itself between illuminated regions and dark regions, we can get some outliers where we compare values that should be near zero to values that are close to zero, but not necessarily zero. Fortunately, when we check out the SSIM results, it tells sort of a different story. The brightest parts are in the unlit regions, or at least the brightest parts corresponding to the metric performance, meaning that the SSIM is telling us that the most structurally similar parts are in the shadowed regions, sort of reinforcing that the percent error is showing us outliers between some of the illuminated parts that should not be in dark regions, but by and large, the performance there is still good and they still look structurally similar. This is reinforced by just the pure outputs from this plot using the median for each of our performance metric values here, which is a little bit more, or sorry, a little bit less sensitive to outliers. We see that by and large, for each of these metrics, they're performing very much similarly to one another. So, just some concluding remarks. I wanted to come back to the comparison between these two plots here. So, we're getting very good shape models compared to before. We are getting good visual performance, but as we move forward, we want to increase the accuracy of our visual performance with MW-NeRF, make it even better than the original visual performance we were having with just visually only trained NeRFs. And now that we have these full underlying shape models, we want to expand what we can do with them, most notably by seeing if we can train models that can generalize lighting conditions or dynamically relight the scene using just a handful of training instances from different lighting conditions. But that does with what we're covering here today. Here's a summary of what we've covered. And if you have any questions, feel free to reach out for me. Thank you for attending my presentation here.